A compound bow is a modern bow that uses a levering system, usually of cables and pulleys, to bend the limbs. The pulley cam system grants the wielder a mechanical advantage, and so the limbs of a compound bow are much stiffer than those of a recurve bow or longbow. This rigidity makes the compound bow more energy efficient than other bows, as less energy is dissipated in limb movement. The higher rigidity, higher technology construction also improves accuracy by reducing the bow's sensitivity to changes in temperature and humidity. The pulley cam system also confers a benefit called let-off. As the string is drawn back, the pulleys rotate. The pulleys are eccentric rather than round, and so their effective radius changes as they rotate. The pulleys feature two cam tracks, an inner cam track which connects mechanically to the limbs or opposite cam, and an outer cam track which the bowstring runs through. As the bow is drawn, the ratio of bowstring payout and bowstring take-up relative to limb weight and leverage of the cams changes. By manipulation of the shapes of these cam tracks, different draw-stroke profiles can be created. A compound bow can be soft drawing with a slow build-up to peak weight on a gradual let-off with a long valley at the end. It can also be hard drawing with a very fast build-up to peak draw weight, a long plateau where weight is maintained, and a quick let-off with a short valley. The let-off itself is the result of the cam profiles having passed center and approaching a condition very similar to a cam lock. In fact, some compound bows, if the draw stops or draw length modules are removed, will self-lock at full draw and require professional equipment to unlock safely. The compound bow was first developed in 1966 by Hollis Wilbur Allen in Billings, Missouri, and a U.S. patent was granted in 1969. The compound bow has become increasingly popular. In the United States, the compound is the dominant form of bow. In literature of the early 20th century, before the invention of compound bows, composite bows were described as compound. This usage is now outdated. Construction of compound bow. A bow's central mount for other components such as the limbs, sights, stabilizers and quivers is called the riser. Risers are designed to be as rigid as possible. The central riser of a compound bow is usually made of aluminum, magnesium alloy, or carbon fiber, and many are made of 7075 aluminum alloy. Limbs are made of composite materials and are capable of taking high tensile and compressive forces. The limbs store all the energy of the bow. No energy is stored in the pulleys and cables. A draw weight generally falls between 10 and 100 pounds, enabling arrow speeds of 150 to 370 feet per second. In the most common configuration, there is a cam or wheel at the end of each limb. The shape of the cam may vary somewhat between different bow designs. There are several different concepts of using the cams to store energy in the limbs, and these all fall under a category called bow eccentrics. The four most common types of bow eccentrics are single cam, hybrid cam, dual cam and binary cam. However, there are also other less common designs, like the quad cam and hinged. Cams are often described using their let-off rating. As a cam is rotated, the force required to hold the bow in position reaches a peak and then decreases as the bow approaches maximum extension. The percent difference between the maximum force encountered during the draw and the force required to hold the bow in full extension is the let-off. This value is commonly between 65% and 80% of the peak weight for recently designed compound bows, although some older compound bows provided a let-off of only 50% and some recent designs achieve let-offs in excess of 90%. The photo on the right shows the axle attaching the limb to cam is mounted at the edge of the cam as opposed to the center. As the string is drawn, the cam turns and imparts force to compress the limb. Initially, the archer has the short side of the cam, with the leverage being a mechanical disadvantage. High energy input is therefore required. When near full draw is reached, the cam has turned to its full extent, the archer has gained mechanical advantage, and the least amount of force needs to be applied to the string to keep the limbs bent. This is known as let-off. The lower holding weight enables the archer to maintain the bow fully drawn and take more time to aim. This let-off enables the archer to accurately shoot a compound bow with a much higher peak draw weight than other bows. However, there are quite a few youth-oriented compound bows with low draw weights that have no let-off and have a maximum draw length deliberately set farther than the majority of young shooters would reach. This effectively makes the bow function very similar to a recurve, with the draw length determined by the shooter's preferred anchor point. This removes the necessity to adjust the bow draw length or use a different bow for different shooters. This type of bow is required for use in the U.S. National Archery in the Schools program. Compound bow strings and cables are normally made of high modulus polyethylene and are designed to have great tensile strength and minimal stretchability, so that the bow transfers its energy to the arrow as efficiently and durably as possible. In earlier models of compound bows, the cables were often made of plastic-coated steel. Comparison to other bow types. Technical advantages. The function of the cam systems is to maximize the energy storage throughout the draw cycle and provide let-off at the end of the cycle. A traditional recurve bow has a very linear draw weight curve, meaning that as the bow is drawn back, the draw force becomes heavier with each inch of draw. Therefore, little energy is stored in the first half of the draw, and much more energy at the end where the draw weight is heaviest. The compound bow operates with a different weight profile, reaching its peak weight within the first few inches of the draw, and remaining more flat and constant until the end of the cycle, where the cams let off and allow a reduced holding weight. This manipulation of the peak weight throughout the draw is why compound bows store more energy and shoot faster than an equivalent peak weight recurve bow or longbow. The design of the cams directly controls the acceleration of the arrow. What is termed a soft cam will accelerate the arrow more gently than a harder cam. Novice archers will typically shoot of soft cam, whereas a more advanced archer may choose to use a harder cam to gain speed. Bows can be had with a variety of cams in a full spectrum from soft to hard. Some pulley systems use a single cam at the bottom of the bow and a balanced wheel at the top of the bow instead of two identical cams. This design eliminates the need for bus cables and instead uses a single string that begins at the cam on the bottom of the bow, travels over the wheel on top, around the bottom cam again, and ends attaching to the top limb. When a compound bow is drawn, the limbs are pulled in toward each other by the bus cables. Unlike a longbow or recurve where the limbs flex in the direction of the bowstring, this difference allows modern compounds to have limbs that are horizontal instead of angle. The horizontal limb configuration minimizes the recoil and vibration felt by the shooter when the arrow is released. The pulley system will usually include some rubber-covered blocks that act as draw stops. These provide a solid wall that the archer can draw against. These draw stops can be adjusted to suit the archer's optimum draw length, which helps the archer achieve a consistent anchor point and a consistent amount of force imparted to the arrow in every shot, further increasing accuracy. Technical disadvantages. There are a relatively large number of moving parts, requires additional maintenance, and creates more points of failure. Warranties for compound bows do not cover dry losing, and it's not unusual for numerous parts, especially the limbs, to be damaged or destroyed after even a single dry losing. If a string or cable breaks when the bow has been drawn, this will have a similar damaging effect on the limbs. Unlike traditional bows, replacing the string or making adjustments to let off a draw length often requires a bow press. Circumstantial advantages. Compound archers often use a mechanical release aid to hold and release the string. This attaches to the bowstring near the point where the arrow attaches, the nocking point, and permits the archer to release the string with a squeeze of a trigger or a slight increase of tension. The use of a release aid gives a more consistent release than the use of fingers on the string, as it minimizes the arrow oscillation, which is inevitable when the bowstring is released directly from the fingers. In tournaments, compound archers usually equip the bows with a sighting system, consisting of a peep sight held within the bowstring that acts as a back sight, and a front sight attached to the bow handle. Some front sights are magnifying and/or adjustable for targets at different distances. Some sights have multiple pins set up for targets at different distances. Stabilizers and dampers are particularly well developed for the compound bow. They allow the archer to hold steadier at full draw, reduce movement of the bow as the arrow is released, and absorb some of the recoil shock that would otherwise be transmitted to the archer's body, especially shoulder and elbow. Circumstantial disadvantages. The relatively low holding weight of a compound bow compared to a recurve bow makes the compound more sensitive to certain shooting form faults when the archer is at full draw. In particular, it's easier for the archer to torque the bow around the vertical axis, leading to left-right errors, and also a pluck-to-snatch release can have more effect. Quantities describing compound bows. Ammo. Standard draw length is the distance from the string at full draw to the lowest point on the grip plus 1.75 inches, 4.45 centimeters, because the draw force may increase more or less rapidly, and again drop off more or less rapidly when approaching peak draw. Bows of the same peak draw force can store different amounts of energy. Norbert Mullany has defined the ratio of stored energy to peak draw force. This is usually around 1 foot-pound per pound, 3048 joules per meter. The efficiency of bows also varies. Normally between 70 to 85% of the stored energy is transferred to the arrow. This stored energy is referred to as potential energy. When transferred to the arrow, it is referred to as kinetic energy. The product of S, E, P, D, F and efficiency can be called the power factor. There are two measurement standards of this quantity, ammo and bow speed. Ammo is defined as the initial velocity of a 35 grams, 540 grain arrow when shot from a bow with a peak draw weight of 270 N, 60 lbf and draw length 76 cm, 30 inches. Bow speed is defined as the initial velocity of a 22.7 grams, 350 grain arrow shot from a bow with a peak draw weight of 300 N, 70 lbf and a draw length of 76 centimeters, 30 inches. Brace height is the distance from the pivot point of the grip to the string at rest. Typically, a shorter brace height will result in an increased power stroke, but comes at the price of a bow that's less forgiving to shooter error and having harsher string slap. Arrows used with compound bows do not differ significantly from those used with recurve bows, being typically either aluminium alloy, carbon fiber, or a composite of the two materials. The exception being wooden arrows, which are not commonly used on compound bows because of the fragility. Most arrows in use today are of the carbon fiber variety. An important distinction arrow-wise between recurve bows and compound bows is that of arrow spine. Compound bows and target recurve bows with fully center-shot cutaway rises tend to be very forgiving in regard to spine selection. Modern compound bows are typically equipped with substantially stiffer arrows than an equivalent draw length and draw weight recurve bow would be. Another Another advantage of the center shot riser is that the arrow need not bend around the riser during the shot. Fine-tuning may be accomplished by adjustment of the arrow rest, or nock point on the string, rather than by changing arrow length and tip weight. Manufacturers produce arrow shafts with different weights, different spines, and different lengths in the same model of shaft to accommodate different draw weights and lengths, matched to archers' different styles, preferences and physical attributes. Arrow stiffness is an important parameter in finding arrows that will shoot accurately from any particular bow, the spine varying with both the construction and length of the arrow. Another important consideration is that the EBO recommends at least 5 grains of total arrow weight per pound of draw weight. This means a bow that draws 60 pounds would need at least a 300 grain finished with tip arrow.